Hey, what's up guys? Today we're finally back to working on Engine Simulator, but before we do that, I'd like to thank BeamNG, Reyna, Meister, Joe, and Bacteria Rancher for supporting me at the Master Mechanic level on Patreon. This is the POWERFIST 212, which is sort of the Canadian version of the Predator 212. It's a single-cylinder engine, and we're going to be using it today to conduct basic testing and collect data we can compare my engine simulation to. To measure the sound pressure emitted from the exhaust, I bought this measurement microphone. In theory, microphones are linear measurement devices, which convert a sound pressure to a voltage. Now, there may be some non-linearity in my USB interface or anywhere else in the recording chain, but for my purposes, this should be accurate enough. The only thing left to do is calibrate the setup, which is what this sound level calibrator is for. It outputs a 1 kHz sine wave and generates a known sound pressure within this cavity. All we need to do is insert the microphone, turn on the calibrator, record a few seconds of audio, and now we have a reference waveform that we can use to calculate the microphone's pressure sensitivity and calibrate our readings. We're more interested in the overall waveform for this video and not necessarily amplitude, but calibrated amplitude measurements did help me to confirm that the simulator's predictions aligned with real engines. So here's my low-budget test rig. After filling up with gas and setting up my control station, we were ready for some testing. For the first few tests, I left the stock muffler on the engine. This engine uses a governor, which is a speed regulating device. It can be bypassed pretty easily by just sticking your hand under the gas tank and moving the throttle manually, but I don't recommend this because the engine is not designed to rev past 3,800 RPM. To make a better comparison, I replaced the OEM muffler with an aftermarket straight pipe exhaust. You'll notice that it changes the exhaust sound considerably, and this is even more obvious at lower RPM. You can hear a direct comparison between the muffled and unmuffled exhaust in this demonstration. The engine is also considerably louder when under load. For legal reasons, I don't want to show how the engine was loaded, but let's just say it involved some wood and a lot of smoke. Notice the difference in absolute magnitude between the engine running with no load and when fully loaded at the same RPM. Alright, now that we have some reference audio, let's move over to the simulation realm. We're going to be comparing two simulators today, the old engine simulator and the new version I'm working on. First, let's listen to the audio from the old engine simulator so we know our starting point. I wouldn't say that it's that bad, especially considering how simple the simulation is, but the inaccuracies definitely show up most when the engine is idling and decelerating. Clearly, those are the conditions under which the gas dynamics in the exhaust become more important. This requires a more advanced fluid simulation to capture. I already implemented a decent high-resolution fluid simulation, but there are some issues with it. I was under a lot of time pressure, so I couldn't put the level of care into it that I really wanted to. It worked and made decent audio, but I didn't fully understand what I was doing, which prevented me from improving it or adding more complex components, like tube junctions. So I went back to basics and studied fluid simulations much more rigorously. This took hundreds of hours of work, and today we're going to look at this new fluid simulation layer by layer to understand it and its limitations. First, let's start off with the simplest possible simulation. For the interior of the tube, we're going to use a very simplistic differential equation solver. For the ends of the tube, which are counterintuitively the most difficult part to simulate, we're going to start with the very approximate valve and outlet model I used in my previous engine simulator video. I'll play a calibrated recording of the real POWERFIST first for reference. The most obvious issue is that it sounds a bit muffled. A more precise way to put it is that the output is missing high-frequency detail, as though it was low-pass filtered at some point. This is unfortunately just a mathematical reality of how fluid simulations work. In this case, we are using a very simplistic partial differential equation solver, which introduces a lot of artificial dissipation into the solution. By artificial dissipation, I mean that the signal is becoming rounded over at the edges as though it's worn down or eroded. There are two main techniques we can use to rectify this. We can either subdivide the simulation into a finer grid, or we can just use a better solver. The first option is simpler, but requires more computation because we need more cells. But since the method is cheap, it doesn't seem like such a big deal. However, for complicated reasons, the performance cost actually grows non-linearly as the resolution increases, quickly making this approach impractical. Brute forcing a bad technique into producing sharp output obviously isn't ideal, so we'll instead look to more advanced methods. High-resolution solvers allow us to get sharper results, with the main downside being a slightly higher computational demand per cell. This doesn't matter though, because we can just use fewer cells to get the same result, so they actually end up being faster. By default, these methods are not stable though, and introduce spurious oscillations into the solution. You can see them here forming near large gradients. This doesn't negatively impact the audio, even though the solution is visually obscured. The real problem is that the oscillations grow and eventually cause numerical instability, which then spreads to the rest of the simulation. These oscillations are unavoidable, and this can be proven mathematically. However, we can circumvent this issue using flux or gradient limiters. A gradient limiter is a mathematical device that pre-processes the simulation input to filter out large discontinuities, though this is somewhat of an oversimplification, as it can also exaggerate certain features. To visualize how it works, imagine we have a one-dimensional simulation which is composed of finite volume cells. If we plot pressure and assume that it's uniform in each cell, we end up with a piecewise constant reconstruction of our domain. Using this input will yield a stable but diffusive solution where a lot of high-frequency detail is lost. In other words, the solution looks softer with less defined features. Using a linear piecewise reconstruction gives a more mathematically accurate solution, but introduces spurious oscillations. Applying a gradient limiter to the slopes of each segment produces a generally accurate reconstruction with only extreme gradients being attenuated. This results in a solution that doesn't have spurious oscillations and is visually more correct. Unfortunately, there is a cost to gradient limiters. Just because a signal looks clean and stable does not necessarily mean it sounds better. I set up this demonstration which shows what happens when we transmit a signal through a tube. Subjectively, the output of the naive, unstable method sounds fairly clean, like a signal that was run through a low-pass filter. The gradient-limited solution, however, has noticeable high-frequency artifacts.
This is a test. This is a test. This is a test. This is a test.
There are numerous gradient limiters, all with slightly different advantages and disadvantages, and I implemented pretty much all of the commonly used variants, but they all exhibit some form of artifacting. This is all simply to say we are reaching mathematical limits to how accurate and sharp the simulation can be. To make sure this was actually a theoretical limit and not simply an implementation error, I implemented multiple fluid simulation techniques, which theoretically must all converge to the same solution, and they do, albeit at different rates. Many of these techniques do not have any code or conceptual commonalities, yet they still give the same answer. So it is very, very unlikely for all of them to be implemented wrong in the same exact way. Therefore, we can rule out any major implementation errors in the simulation. Most of the artifacts that remain likely cannot be fixed without much more advanced methods, or they must be worked around cleverly. After adding the high-resolution solver, the audio from our simulated POWERFIST doesn't sound as muffled as it did before. For most of the comparisons going forward, I'm going to show the audio from the previous step first, followed by the audio clip showing the improvements. Instead of sounding muffled, it now sounds like we've boarded an alien intergalactic vessel, obviously with aliens still on board. I want to emphasize that the simulation is definitely implemented correctly. I didn't purposefully make it sound ridiculous for dramatic effect. The confusion that you're experiencing right now is the same confusion I experienced while working on this. Imagine spending hundreds of hours building a simulation, making sure it was correct, only to find that this is the output. Clearly, something is missing, but you don't know what it is. This trial and error process of figuring out what needed to be added to the simulation is where the vast majority of my time went. To give you some idea of how much work this took, I have rendered almost 7,000 individual audio clips using this simulation, and I've listened to every single one. That's around 30 hours of just listening to clips like this. This is this. There were definitely times while working on this project where I started to believe that my goals were impossible to achieve, and it's part of the reason why this video took so long to create. For the rest of the video, just keep in mind you really have to wait until the end for the simulation to reach its final form. And even then, just remember it's still a simulation and will never be exactly like real life. I know a lot of people have very high expectations for my work at this point, but I'm sorry to say that we might be reaching theoretical limits of what can be achieved. Anyway, let's try to fix this audio. The most logical place to start would be the valves and outlets, because the boundary condition for valves I created previously is definitely wrong, and I knew it at the time. It was just meant to be a simple, temporary implementation until I replaced it with something more accurate. The model I replaced it with is a classic valve model described by Benson, one of the forefathers of engine simulations. Benson also gave an algorithm to solve the nonlinear equations of this model, but I couldn't get it to work well, so I created my own algorithm with better performance and convergence properties. I say this very casually, but this on its own took over 100 hours of work, and I might discuss this algorithm in its own video at some point. So here's what it sounds like with this new valve model. The sound has improved slightly, but our simulation does not have enough dissipation, leading to this excessive resonance. Real tubes dissipate energy via friction and heat loss. If we add the friction and heat transfer simulation from the last prototype I built, it does sound a bit better. I realized, however, that the heat transfer model was implemented incorrectly. I overlooked this at the time because I didn't think that heat transfer had significant effects on sound. Some papers even omitted heat transfer and claimed that it didn't affect accuracy that much. This might be true in terms of overall accuracy, but I did notice that it had a significant impact on the subjective quality of the sound, as can be heard in this audio sample. The simulator is also capable of handling different materials with different heat conductance properties, and even the surface finish can be specified, which can be used to model things like cast iron manifolds. The next issue to address is turbulence, or the lack thereof. Turbulent flows form at the valve, within the pipe itself, and at the outlet, and I believe this is partially responsible for the characteristic fuzzy pulsing sound that engines generate. Turbulence is extremely complicated and impossible to fully simulate in one dimension, but I implemented a simple model anyway. It needs a bit of tweaking, and it is pretty subtle, but I think it's fine for now. So as far as following the primary literature on engine simulations, this is as far as it'll take us. However, something is not quite right. This problem becomes evident if we try driving an audio signal into a tube.
This is a test.
This is a test. This is a test. It sounds very strange, and what's even stranger is that this problem only becomes worse as the simulation quality is increased.
This is a test.
This is a test. So what's going on here? If we look at a spectrogram of the signal, we see these lines at regularly spaced intervals. This is a test. These correspond to the resonant frequencies of the tube, which primarily depend on the tube's length. For example, here's a long tube. This is a test. And here's a short tube. This is a test. I have these lengths of tubing, and you'll notice that talking into them in real life doesn't cause them to resonate as intensely.
This is a test. This is a test.
I noticed something similar in the data collected from the POWERFIST test. You can clearly see a peak at the fundamental frequency of the exhaust tube, but no other harmonics seem to be present. My theory is that the simulation of the tube boundary is too perfect, and virtually any input signal excites basically all resonant frequencies at the same time. In reality, high-frequency components do not get reflected as efficiently, preventing the formation of high-frequency standing waves. I created a model that accounts for this, and it improved the predicted waveform considerably.
This is a test.
This is a test.
This is a test.
This is a test. Now, let's compare our final simulated result to the real recordings. It's a bit hard because the real engine produces a lot of mechanical noise. I'm going to alternate between the muffled and unmuffled output, which helped me to mentally isolate the exhaust sound, which is what we're interested in. Alright, let's try a more complicated engine. In my second ever engine simulator video, I showed a Harley Davidson engine. This was probably one of the worst engines in that video because the simulator just wasn't capable of modeling the complex dynamics in the exhaust tubes. So let's see if it sounds better in the new simulation. Alright, I had a whole section of this video dedicated to discussing pipe junctions and larger engines, but I decided to cover it in a separate video instead because it still needs a bit of work. However, I will share some short clips of a few engines that use the new junction simulation. Please remember, these are works in progress. We will come back to improving the simulation and the audio output, but we've run out of time in this phase of development, and I need to move on to something else. It's also extremely tedious to continue testing in this haphazard environment. We really need a user interface to design engines, set up test cases, and of course, so we can actually get the simulation released on Steam. So that's what I'll work on next, and I do plan to return to a semi-regular upload schedule on YouTube. I do have the store page set up if you guys want to wishlist the game. I know that a lot of people want a release date, but I only give release dates that I'm 100% sure are doable, and it's too early to make any predictions with confidence. Once the program is released though, I will continue to refine the simulation and add features, but for now, it's functionally complete and supports everything I needed to support for an initial release. Thanks to my dad and my brother for helping me set up and record the engine testing segment. My brother has actually started his own YouTube channel, which I strongly recommend checking out. The link to that is in the description. Thanks to my Patreon supporters for making this whole project possible and being very patient with my perfectionism. And of course, thank you for watching. I'll see you all next time.